I want to conclude this first module by talking about an interesting experiment that took place in the 1800s, performed by Joule and Thomson, two of the real titans of thermodynamics of that period. Joule, you already know about, having lent his name to our units for energy. Thomson actually later became Lord Kelvin, and that's where the Kelvin temperature scale is derived. So these guys are both preeminent scientists. The experiment they were doing was actually derived in part from earlier experiments that Joule had done, where he was trying to understand temperature changes in gases that expanded. And he did some simple experiments of gases expanding into a vacuum and tried to measure the temperature difference, and really didn't detect any temperature difference at all. Yet some of the theories that he was contemplating suggested that there should be some temperature difference. So he and Kelvin, or he and Thomson together, devised this experiment. Now, I'm not very good at explaining this experiment, so I'll explain that right off the bat, but I want to do my best so that you can get an appreciation for what it is they did. I'm showing you three pictures here that show different snapshots of the experiment, and we're going to start here on the left-hand side, and what we have is a pressure 1 that's exerted on the piston that's on the left-hand side. We have a gas occupying a volume V1 there. On the right-hand side, we have a pressure P2 that opposes that, and we'll say right off the bat that P2 is going to be less than P1. So in other words, we have a large pressure pushing here from the left and a smaller pressure opposing it on the right. So what we would ordinarily expect to see is that the gas that's contained in here is going to expand into the right-hand side because the pressure that it's pushing against is weaker there. Now, what is this thing in the middle? What I'm drawing here is a porous membrane that allows the gas to go through, but it doesn't allow it to just flow through freely. So what happens then is that the gas, as it's going through there, is slowed down, and it keeps this experiment basically at equilibrium at all times. Even though we have movement, we have a driving force that's going to drive gas from the left side to the right side, it's always at some equilibrium. And in fact, the conditions set up for this experiment were to make it an adiabatic expansion of the gas, so we can assume that the heat exchange with the environment is going to be zero in this case. Now, here at the midway point, we still have pressure P1 pushing on the left-hand side of this piston, and pressure P2 over here. Those are going to be held constant in this experiment. And what we're really caring about, because this is what Joule cared about, is what is the effect that this has on the temperature. All right, so some of the gases are finding their way through this porous membrane. They're getting to the right-hand side from the left-hand side. And as they're flowing through, they're presumably changing in temperature. So we're going to be measuring the temperature over here, which is fixed by the experiment, and the temperature over here, which is derived from the expansion process. Now over here, the expansion has completed. We still have pressure P1 pushing on this side of the piston. We still have pressure P2 pushing on this side of the piston, but now it's all pushed all the way to the porous membrane, and we have our gas now entirely on the right-hand side, and it's filling a volume V2. Now, because this pressure is less than the initial pressure V1, we can assume that V2 is greater than V1 because it has less pressure that's pushing against it. So our real question now is, how do we track what's going on in this experiment? Now, a really interesting aspect of this experiment is the following. Since this is isolated from the environment and there is no heat exchange with the environment, what we're going to have is that the internal energy in this case, which ordinarily is a contribution from both heat and work, is entirely due to work in this case. We're doing work on the gas, pushing it through this porous membrane into a side where it has less pressure. So in this case, the work is going to be the change in the pressure times volume, and I need to put a minus sign in front of that because remember, this is how we characterize the work in this case. So the work is actually going to be equal to the final pressure and volume, which is, I'm going to put a negative sign out there again, P2V2 minus the initial pressure P1V1. This would be the change in the work. And this is going to be equal to our change in internal energy, which we can write as U2 minus U1. All right. Well, interestingly, if we take this expression and rearrange it a little bit, what we'll find is that U1 plus P1V1 is equal to U2 plus P2V2. All right, well, why does that interest us? Well, remember the definition of enthalpy is U plus PV. So what this expression is telling us is that the initial pressure and the final pressure, the initial enthalpy and the final enthalpy are the same. So in other words, the change in enthalpy for this process is zero. And that makes this entire process what is called an isenthalpic process. That is, a process in which the enthalpy doesn't change. This is very unusual, and I will say that in nature we don't really have many circumstances where we might see an isenthalpic process. So this is a purely put together by this experiment, and it's an artifact of this experiment. Now, what is observed in this case? Well, when they ran this experiment, for many gases that they ran, so we have on the left-hand side a temperature T1, and on the right-hand side a temperature T2. What is the relationship between these temperatures? Well, they found for the vast majority of substances, what tended to happen at lower temperatures, lower initial temperatures, is that there was cooling of the gas as it went through. All right, so there was a cooling effect that was observed. Now this is true of all of the gases except for a couple, and the ones that it didn't cool for were things like hydrogen gas and helium gas, and neon, I believe, is another one. And these are all gases that have very weak attractive forces, so weak intermolecular forces, which is a clue here for what's going on. So in effect, what they believe was happening is that as this device was doing work to push the gas through this porous membrane, the work that was performed on the gas was simply being used to overcome the attractive forces. So since that work was overcoming the attractive forces, it led to a net cooling effect on these gases. Now it turns out that when you go to higher temperatures with these same gases, this actually converts over to a warming effect. At higher initial temperatures, and when I say lower T and higher T, I'm really referring to T1 in this case. T2 is what we're measuring in the experiment. At the higher temperatures, these molecules are moving fast enough to overcome those attractive forces. So the work is no longer being used to pull the molecules apart from one another. They're already apart. In effect, what's happening is the work that's being done on the gas is converted into heat. Now, this is not heat that came from the environment. This is heat that came from within the system. So we have basically taken work and we've turned it into heat, and the effect that this has is to warm the gas. So this is a very interesting experiment in that it's helping us learn a little bit about the inner workings, if you will, of the first law of thermodynamics. Now, the temperature at which this conversion takes place is called the Joule-Thomson temperature. And I'm going to call it T sub JT, JT for Joule and Thomson. And so it's the temperature at which the substance converts. The work goes from cooling to heating for this substance. So it's going to be a characteristic temperature for every different substance. Now, another way that we can characterize this is by defining what is known as the Joule-Thomson coefficient, and it's given the symbol mu, and I'll go JT again as the subscript to identify it as a Joule-Thomson coefficient. And it is basically a measure of how much the temperature changes based on the pressure difference between the two sides of this experiment. Remember, the pressures 1 and 2 are set in advance in this experiment, and the change in the temperature is going to be the difference between the measured temperature at the end and the temperature that we started with at the beginning. And since this is taking place as part of an isenthalpic process, that means that the thing that's held constant here is the enthalpy. So this is a really unusual sort of partial derivative that we have here, and one that we don't encounter, I will say, regularly in the common course of things. Now, we could take this and use our various manipulations for partial derivatives to get something else. So, for example, I could say, I'm going to use the cyclic permutation and write del T del P at constant h could be multiplied by dP dH at constant T and multiplied by dH dt at constant P, and that's going to be equal to -1. And that's going to lead us to understand a different relationship, but I want to recognize that this thing here is simply the heat capacity at constant pressure. So if I divide by that heat capacity at constant pressure and I divide by this, I can now flip this around and I'll end up with a relationship that says dt dP at H is equal to 1 over the heat capacity at constant pressure, and I need a minus sign in front of that, times the inverse of this derivative, which would be dH dP at constant temperature. And so this is another way that we can express the Joule-Thomson coefficient using a little bit different derivative. And in fact, this derivative itself can be written a different way, and I'll show that on the next slide. Let's get to that next slide. All right, so I wrote before that the Joule-Thomson coefficient could be written as -1 over Cp, times the partial derivative of the enthalpy with respect to pressure at constant temperature. And this actually, if you do a few more manipulations, you can show that this is equal to, and now I'm going to put a positive sign in front of this, the volume over the heat capacity at constant pressure times this interesting collection of constants, where this is the isobaric thermal expansivity that we talked about in an earlier video. This is the temperature. So notice that here we have an interesting relationship that, depending upon the values of alpha and of temperature in this case, this coefficient mu can be either positive or negative. And in fact, when it is positive, this is what corresponds to a cooling effect when the gas expands through the porous membrane. When it is negative, this corresponds to a warming effect. Now, just so you can see what this really looks like, this is over here is an example of what some data might look like. Most of this data pertains to nitrogen, so all of the curves except for this one, that one corresponds to H2, all of these are for nitrogen at different pressures. So the one out here is at nitrogen at 1 atmosphere, and then we've increased the pressure as we go down here, so pressure increases. Now, what is this showing us? Well, notice that out here there is a temperature at which these things cross 0. So this is the temperature at which mu goes from being positive to being negative. So that's the Joule-Thomson temperature. That's the place where it's going to convert from being a cooling effect to a warming effect. And you'll see for hydrogen out here, that temperature is much lower than it is for nitrogen. So that explains why at room temperature one observes hydrogen to be a warming effect, because it's already negative. The Joule-Thomson coefficient is already negative out here for hydrogen gas. For nitrogen gas, though, it's positive, so it shows the cooling effect. Now, why would we care about all this? Well, it turns out that this Joule-Thomson experiment is in effect the same way that we generate refrigeration these days. So by taking a gas and expanding it appropriately through a porous membrane of some sort, or by throttling the expansion of the gas, we can actually cause it to cool off, and that cooling effect can be quite extreme, and that's what leads to refrigeration. And we find that particular kinds of gases, particularly halogenated hydrocarbons work really well with this because they don't have the properties that would cause them, like hydrogen, to warm when they get to that. They have a relatively high Joule-Thomson temperature. Now, another way that we can express all of this, and this is a diagram that's shown in the text material that's provided with this lesson, is to map out what values of pressure and temperature correspond to a positive value of the Joule-Thomson coefficient. So in other words, this shaded area is where we observe cooling of the gas. So whenever the pressure and the temperature is in this particular segment, it's kind of an odd shape here in the pressure temperature diagram, but this is where we're going to see cooling, and everything else out here correspond to pressures and temperatures where we're going to see the gas warm as it goes through that throttle. So I hope this has made some sense. I will tell you that I'm not going to insist that you understand the details of the Joule-Thomson experiment. I think it's something you should know about, and you should see it as an application of how we can learn something about the physics of a system by playing with these partial derivatives a little bit and understanding how we can get information from them. In addition, you can learn something about the Joule-Thomson coefficient and what it tells you about different gases and their capabilities for cooling and being used as refrigerants.